Welcome to TechNova Podcast.
For like 30 years, scientists have essentially been, they've been rigging the cosmic casino to make sure Earth hits the jackpot.
Right.
We know when you look up at the night sky, it is incredibly easy to just assume that our little blue marble is a freak accident.
Yeah, absolutely.
We have this quiet assumption that standing on a rocky planet situated at the perfect distance from a star with an atmosphere and liquid water is this 1 in a billion cosmic lottery ticket.
Oh, for sure. It feels special.
Right. But what if the game was never rigged? What if our planet is exactly what you would expect the universe to build on its default setting?
It completely reframes our entire understanding of planetary science. I mean, the prevailing assumption, even within the highest levels of astrophysics, was always that a solar system structured like ours had to be anomalous.
Anomalous, like weird.
Yeah, like weird. The architecture of Mercury, Venus, Earth, and Mars just seemed too fragile, too specific to be a regular occurrence in the galaxy.
Well, we are looking at a piece of science journalism today
Yeah,
that absolutely shatters that assumption.
it really does.
We are pulling from an article by veteran science journalist Bruce Dorminey, published in Universe Today. The piece is dated August 21st, 2026, and the title really it lays out the thesis perfectly. It's called New Solar System Models Show Earth is No Fluke.
It's a great title. And Dorminey is reporting on some highly disruptive research that just debuted at the Origins 2026 conference in Paris.
Yeah.
The focus is on a planetary scientist named Nader Haghighipour. And he basically took 3 decades of established planetary modeling, identified this massive methodological blind spot, and demonstrated that a planet like Earth is a highly natural, almost inevitable outcome of fundamental physics.
Okay, let's unpack this. Because to understand how Haghighipour revolutionized the field at this Paris conference, we need to talk about that blind spot.
Right.
What have scientists been doing for the last 30 years that effectively constrained our understanding of the solar system?
They were over-constraining their parameter space.
Okay, what does that mean?
So for the past 3 decades, computer models simulating the formation of planetary systems were essentially reverse engineered. Haghighipour pointed out that scientists were making fundamental core assumptions based on the planetary architecture we already live in.
Oh, I see. So they were working backwards.
Exactly.
They were starting the simulation with the goal already in mind.
Building a model to fit a known reality sounds logical on the surface, right?
Yeah, you want it to match what we see.
Right, but computationally, it places this enormous straitjacket on the physics. If you tell a simulation that it must eventually produce a solar system with an Earth at 1 astronomical unit and a Mars a little further out, you are forcing the math. You are artificially constraining the chaotic dynamics of the universe to force a very specific, preconceived outcome.
I mean, it sounds like baking a cake where you start by strictly defining it. Has to be a 3-tier chocolate cake, rather than just throwing raw ingredients into a bowl, turning on the physics oven, and seeing what actually bakes.
That is a perfect way to put it. The physics oven is going to ignore all the other possible configurations it could have naturally produced with those ingredients.
Just because you told it to.
Simply because you programmed it to only care about the chocolate cake.
Wow.
And Haghighipour recognized that this methodology had just hit a concrete wall. After 30 years of simulating terrestrial planet formation with these rigid guardrails, the science wasn't actually discovering anything new.
It was just confirming what we already knew.
Yeah, the modeling was just validating our own biases about our solar system. It couldn't be pushed any further to yield fresh insights into how solar systems actually form in the wild.
In the wild, yeah. So how does this new research from Origins 2026 tear down that wall? Like, what did Haghighipour and his colleagues actually change about the methodology to get away from that flawed baking method?
They adopted a complete blank slate approach.
A blank slate.
Yeah. Haghighipour stripped away every single constraint and went all the way back to the very beginning of the solar system's formation. He made absolutely 0 assumptions about the final planetary architecture. He didn't instruct the computer program to build an Earth or a Venus or anything resembling our neighborhood.
He just feeds raw data into the model.
Just raw data.
And according to the Universe Today piece, the environment he is feeding into this blank slate is a protoplanetary disk, but specifically one with a non-uniform distribution of solid material.
Yes. That non-uniformity is the critical engine for everything that follows.
Why is that?
Well, in the early days of a stellar system, you have this swirling disk of gas and dust rotating around a young star. If that disk is perfectly uniform and smooth, the physics stall out.
Oh, because everything is balanced.
Exactly. Everything is balanced, nothing bumps into each other in a meaningful way. But Haghighipour populated these simulated disks with a non-uniform, clumpy distribution of planetesimals and planetary embryos.
So we have cosmic rubble, asteroids, rocks, and these larger moon-sized planetary embryos that have already started to coalesce, all distributed completely randomly.
Completely randomly.
Because fundamentally, nobody knows the precise starting arrangement of our own solar system.
Right. Nobody was there to document the initial distribution of mass billions of years ago.
Right.
And by acknowledging that ignorance, Haghighipour freed the models.
Oh, that's interesting.
Instead of guessing one specific starting arrangement to try and force the creation of Earth, he ran simulations using totally random starting points over and over again, and let the unyielding laws of physics drive the evolution.
Just letting physics take the wheel entirely.
Taking the wheel.
But we have to talk about the scale of what he actually accomplished here, because the technological leap from the old way of doing things to this new blank slate method is staggering.
It is mind-blowing.
He didn't just run this random simulation a dozen times to see what happened. He ran more than 1,000 simulations of the late stage of terrestrial planet formation.
Over 1,000.
Over 1,000 distinct solar systems baked from scratch.
The sheer computational power required to do that represents a massive paradigm shift in astrophysics. The article points out that under the old, highly constrained methodology, running just one complex planetary interaction simulation could take 6 to 8 months of continuous computing time on massive systems.
6 to 8 months. For a single data point.
A single simulation run, yes.
The friction of the scientific method there is almost unbearable. I mean, if a power grid blinks in month 7, you lose your entire year's work.
Oh, it would be devastating. And that extreme computational cost is exactly why the previous models were so constrained.
Oh, of course.
You couldn't afford to run a simulation for 8 months if you weren't guaranteed to get a recognizable solar system at the end of it.
You needed a sure thing for that kind of time investment.
Exactly. But thanks to the exponential growth in processing power, Haghighipour and his team ran these new, infinitely more complex, unconstrained models in just 6 to 8 weeks on current laptop computers.
Laptops.
Going
from supercomputers grinding for the better part of a year to a machine you can commute with crunching the chaotic birth of a solar system in a matter of weeks.
It's wild.
That unleashes a totally different kind of science. But I am going to push back slightly here on the mechanics of these simulations.
Okay, sure.
If the starting points of these protoplanetary disks are completely random, just clumpy, non-uniform distributions of planetesimals, and we're just letting a laptop crunch the physics of these things crashing into each other, doesn't chaos just breed more chaos? How do we get a neat, orderly solar system with nice circular orbits out of a completely random, violent starting condition?
What's fascinating here is that the fundamental forces of the universe, specifically gravity and the conservation of angular momentum, act as an incredibly efficient cosmic sorting mechanism.
Sorting mechanism.
Yes. You are correct that the initial environment is violent. Planetary embryos are colliding, shattering, merging, and gravitationally throwing each other completely off course.
Just a giant cosmic demolition derby.
Exactly. But over millions of years of simulated time, those chaotic, inelastic collisions actually start to cancel out the extreme erratic orbits.
So the chaos essentially averages itself out into order.
Over a long enough timeline, yes. The material is forced into a relatively flat plane, and the orbits circularize and settle into stable resonances.
Wow.
But the element of chaos remains vital, because Haghighipour's 1,000 simulations emphasize that tiny, seemingly insignificant variations in the initial state dictate the final architecture of the system.
It's the butterfly effect on a cosmic scale.
Exactly, the butterfly effect.
Like a cluster of planetesimals being just a fraction of a degree further from the host star cascades into a totally different final planet.
Even a minuscule difference in the density of one planetary embryo alters the gravitational tug-of-war for the next 10 million years.
Oh, man.
That is why running over 1,000 simulations was the only way to do this. It allowed the team to map the statistical probabilities of what physics inherently wants to build, rather than just looking at one random outcome.
So they run the 1,000 simulations. They drop the constraints, let the random clumps of cosmic rubble smash together under the laws of physics, and wait for the angular momentum to sort the chaos in the stable planets.
Right.
What are the results? What actually pops out of these blank slate laptops?
The results completely dismantle the idea that our solar system is an anomaly.
Okay.
Haghighipour found that the formation of an Earth-like planet at 1 astronomical unit, which is the exact distance our Earth sits from the sun, is a highly natural outcome of the evolution of our solar system.
It's the default setting.
Yes.
It's not a freak accident.
When you let physics operate without forcing its hand, the protoplanetary disk organically produces a terrestrial world right where we are sitting today.
Here's where it gets really interesting, though, because it isn't just Earth that reliably pops out of this chaotic simulation.
Right.
The models kept spitting out our sibling planets as well.
They did.
The Universe Today article highlights that Venus appears about 28% of the time in these simulations.
Nearly a third of the time.
More than a quarter of the time, complete random chance in physics output of Venus that successfully maintains its orbit.
Furthermore, the models showed this Venus-like planet sometimes forming squarely within the habitable zone of its star, and sometimes forming slightly outside of it,
Oh, wow.
which perfectly mirrors the actual atmospheric and orbital dynamics of our real-world Venus.
And Mars makes an appearance, too.
Yes, it does.
The data showed Mars popping up a number of times as a small, rocky object resting right in the general vicinity of its current orbit.
Synthesizing this data paints a profound picture of our place in the galaxy. By utilizing a blank slate and letting the immutable laws of physics dictate the terms, the universe repeatedly constructs a planetary neighborhood that mirrors our own.
So it's not a one-off.
No, you don't need a highly specific magical starting arrangement to get an Earth, a Venus, and a Mars. The basic gravitational mechanics of a standard protoplanetary disk frequently output this exact type of architecture.
Which means the real estate is incredibly common.
Very common.
If the physics of the universe are hardwired to build Earths, the natural progression of this research has to point toward the search for life.
Absolutely.
We are essentially scaling this laptop simulation beyond our own solar system to the rest of the galaxy.
Haghighipour takes the data from these 1,000 simulations and applies it directly to the exoplanet search. Because his models prove that Earth-sized planets, including small super-Earths, located right in the habitable zones of their stars, are a highly common outcome.
Yeah.
He argues it is entirely logical to consider that earthly life is also common.
I mean, if the universe is constantly building the exact same house, it makes sense that the same kind of tenants would move in.
That's a great analogy. However, Haghighipour is highly pragmatic about our current technological reality.
Okay, how so?
He notes in the piece that finding life on other planets remains an incredibly complicated endeavor, largely because our technology is simply not at the level required to definitively detect it.
Right. We can't just take a picture of a tree on another planet.
Exactly. We have the capability to spot these exoplanets, but confirming active biological processes from light years away is a hurdle we haven't cleared.
Which brings up a really profound philosophical point Haghighipour makes in the article regarding the nature of life itself.
It's a very deep quote.
Yeah, he says, after life originated, we don't know how and we'll never know, life developed branches and bifurcated so that it could find a way to stay in sync with Earth's evolution.
It is a radical departure from viewing biological evolution merely as a series of random mutations competing in a vacuum.
Yeah, usually we just think about life competing with other life.
Right. But he is suggesting that the primary driver for life's survival is geological synchronization.
Synchronization.
Life branches out in a desperate, continuous effort to remain perfectly tuned to the geological, atmospheric, and chemical evolution of the specific planet it inhabits.
So the planet drives the bus.
Yes, our biology is entirely a reflection of our planet's chaotic history.
I'm going to play devil's advocate for a second here.
Yeah.
Because if our technology isn't actually good enough to detect this life out there right now, why does it matter that a laptop simulated the real estate? Like, what is the practical takeaway for the listener today if we are just generating virtual space dust and philosophizing about biology we can't even see?
If we connect this to the bigger picture, this study transcends just alien hunting. It is about deeply understanding the exact frame-by-frame recipe for planetary habitability.
Frame by frame.
By running these unconstrained simulations, the scientific community isn't just celebrating that an Earth-like planet formed, they are tracking the precise physical processes of that formation over millions of simulated years.
Oh, I see. So they can watch it happen.
They are watching how a chaotic cloud of non-uniform rubble eventually coalesces, circularizes its orbit, and develops the stability required to support liquid water.
It's about diagnosing the mechanics of our own home.
Precisely. Understanding that exact sequence of chaotic collisions and gravitational sorting is crucial for understanding our own planet's history.
Yep.
It teaches us about Earth's specific vulnerabilities and exactly what physical thresholds must be crossed for a world to become and remain habitable.
Because things could have gone wrong.
Very wrong. We can't understand the fragility of our own biosphere without understanding the brutal physics that forged the rock it sits on.
So what does this all mean? When we look back at the Origins 2026 conference, the 1,000 blank slate simulations running on laptops, the 28% Venus generation rate, where does this paradigm shift leave us?
It leaves us with a totally new baseline for astrophysics. I believe the absolute bottom line of this research is captured perfectly by Haghighipour's final quote in the article.
Which is?
There is no reason to believe that our Earth is a fluke.
Wow.
The physics of the cosmos are practically hardwired to manufacture worlds just like ours. We are not a statistical error. We are a standard expected product of the universe.
We are just the universe doing what it does best, sorting chaos into order. It takes away that feeling of isolation you get when you look up at the night sky. We want to thank you for exploring the mechanics of the cosmos with us on this deep dive.
It has been a fascinating look into how shedding our own assumptions allows the science to finally breathe.
But before we fade out, we want to leave you with one final thought to mull over, something that builds directly on the implications of today's deep dive. We learned today that tiny, almost imperceptible variations in a solar system's initial conditions create vastly different final planets. And we learned from Haghighipour that life's ultimate survival mechanism is simply branching out to stay in perfect sync with its host planet's specific evolution.
Right.
So imagine those simulated solar systems where Venus-like worlds or entirely different super-Earths formed from a slightly different distribution of rubble. If life's only objective is to constantly sync up to its planet's chaotic history, a geological history so complex we can barely even model it on our best laptops, what wildly different, totally incomprehensible branches of evolutionary life might be out there right now, perfectly in tune with a chaotic planetary evolution we couldn't even begin to comprehend? Keep looking up.